And those infrasonic waves, they can travel very long distances. Do y'all know the animals that communicate by these? Whales, yeah, even dolphins too, but more so whales will communicate by these infrasonic waves. I remember when I was a kid, we got National Geographic. Did you ever get National Geographic? Actually, we didn't get it. Like, my mom got it from the houses where she worked, and so I remember I had a big stack of them, and one of them had a record in it that had sounds of the whale. So I remember as a kid just listening to this recording of the whales. You ever hear that before? The sounds that whales make? But it was one of those floppy records that they would put in magazines back in the early 80s, late 70s. Anybody remember those? They're like giveaway records. No, they were square. They weren't round because they just printed them on like a sheet of plastic. They were kind of cool. You get them free in magazines. Okay. Ultrasound equipment. Uses a frequency of about 20 million hertz. So a lot more, 1,000 times what we can hear. That's usually given in megahertz. So 20 million hertz is 20 megahertz. The capital M means mega or million. These vibrations are absorbed very quickly. So whereas the ultrasonic, or the infrasonic rather, can travel really long distances, the ultrasonic travels very short distances. The infrasonic can travel through the ocean, you know, almost around the world almost, or over many, many hundreds or thousands of miles. But ultrasound waves travel very short distances, on the order of just, you know, a few centimeters maybe. But that's useful still for what we need to do for ultrasound imaging. Okay, let's try a few clicker questions. Vibrating string produces a sound of a certain pitch. What happened if you increase the mass of the string? Or if you increase particularly the mass density of the string? What happens to the pitch of the sound? All right, let's stop at 43. Awesome. A is right. Let's see, what is it? The frequency is 1 over 2L square root of, what was it, T over mu? I think that's right. Isn't that the right equation? Yeah, 1 over 2L square root of T over mu. And mu is the mass density. If this goes up, that means that the frequency will go down. But you probably know that intuitively just from knowing how instruments look. On a guitar, a bass guitar, the thicker string is the lower string. Same is true on a 6-string guitar. That's true on pianos. That's true for any string instrument. Hey, my dad, when I was a kid, he got fired from the calendar factory where he worked. All he did was take a day off. Okay, the speed of a wave depends on which of these? The frequency, the wavelength, or the medium? I'll remind you the equation. V is equal to frequency times the wavelength. So what does the speed of the wave depend upon? All right, let's stop at 30. 30. Ah, I was tricking you, wasn't I? Like writing that equation? Did that trick you? Some of you are tricked. The velocity is not dependent on either the frequency or the wavelength. It's only dependent upon the medium. So C is the right answer. Remember, if I change the frequency, for example, if I increase the frequency, this stays constant, but the wavelength will decrease. So if I have a high frequency wave, it looks like that with a very short wavelength. But if I have a long frequency wave, it looks like that with a smaller frequency. You can see the frequency on these waves just by counting the number of peaks. And so there I have 2 peaks, whereas here I have 1, 2, 3, 4, almost 5 peaks within the same distance or within the same time if I was looking at a history graph. And so the one with more peaks showing has the greater frequency. The lowest pitch a person can hear is which of these? All right, let's stop at 28. Good. B is right. Make sure you know the lowest and the highest. So the lowest is 20 hertz. The highest is 20,000 hertz. What do you call a dinosaur with an extensive vocabulary? A thesaurus. Good guess there. So true or false? Microphones and speakers work by the same mechanism. Is that a true statement or is that a false statement? All right, let's stop at 23. 23. Okay, A is right. That is a true statement. Microphones and speakers do work by the same mechanism. They have some diaphragm that vibrates that will either cause a sound or detect a sound that has caused that vibration. So that they work mostly by the same mechanism. In fact, if you've ever had one of those little microphones on your on your computer, if you accidentally hook it up as a speaker instead, you'll get a little penny sound out of it. It's not a very good sound, but you get a sound out of it regardless. All right, let's look at A&P of speech production. I kind of like this section. It's kind of interesting how the human produces sound. There's no audiologist in here, though, right? Are there? Or speech therapy? There are? A handful of you? Okay, cool. All right, so speech is caused by the movement of air. Past the vocal cords. The air is forced past the vocal cords because of the diaphragm. Remember, your lungs aren't muscles, right? Your lungs can't move by themselves. So the way they expand or contract is by making the chest cavity get bigger or smaller. And you can force out air by your diaphragm, which pushes up on your lungs. So your diaphragm is the way that you force air out of your lungs past your vocal cords. And then the diaphragm can enlarge or shorten the chest cavity. Make it bigger or make it smaller. And if you remember back to our chapter 3, I think, that this was all an application of Boyle's law, that PV is equal to a constant value. So if the volume goes up, that means the pressure goes down. If my volume gets bigger, the pressure gets smaller inside of that volume. And then you'll have a high pressure that will rush in, and then vice versa. People generally breathe 12 to 15 times per second. Or excuse me, per minute. That would be fast, wouldn't it? 12 to 15 times per minute. when in normal activity, and then air moves from the lungs. You need to know sort of the path that air takes in order to produce speech, just the basics of it. And I'll probably have a picture online, on the test where you have to label those different parts. So air moves from the lungs through the trachea. It's also called the windpipe. And then to the larynx, which has the vocal cords. And this is the Adam's apple. So this thing right here in your neck, you can feel it. Can you feel it? It's more pronounced in men. Women, you still have it, of course, but you just can't see it as well. But this thing is your Adam's apple or your larynx, and inside of that are your vocal cords. In fact, put your hands on there. You feel the vibrations? You don't feel them because you're not doing it. Okay. So the vocal cords vibrate when you make sounds. You can feel that. The vocal cords these are also called the vocal folds, as they call them in your book, I think they call them that in your book, are inside the larynx. And that just protects them and moves them with cartilage and muscle. I have a little diagram here of your vocal cords. This is when they're abducted or they're opened up for you to breathe. That's when your vocal cords are apart from one another. But then when you're speaking, your vocal cords are snapped together. So kind of like two sheets of paper, or always do one sheet of paper. It makes them vibrate. I'll show you something else a little bit later. But it causes them to vibrate, kind of like a, what's it called, a kazoo, when you have a kazoo. So it causes them to vibrate, and then they're adducted or pulled together to speak. The vocal cords are actually muscles. That can open or close depending on the situation. And the space between the cords is called the glottis. So you have your cords right here. Whether they're open or they're closed, this space in between the cords is called the glottis. When you're whispering, your glottis is open, or your cords are open. When you're breathing, it's open. And when you're speaking, that means that they're closed, or they're closed more tightly. So when you're whispering, that's why it sounds so breathy. Like when, hey, what's going on? It sounds like you're sort of breathing. Those sound very similar. That sounds kind of creepy, doesn't it? That sounds very similar because your vocal cords are doing basically the same things. They're open during that time. And then when you're speaking, they're closed. A glottal stop is when you close the glottis. I remember my mom died about 7 or 8 years ago. They said it was COPD, which is often means they don't really know what the heck is wrong, and they didn't really know what the heck was wrong with her. But I remember she had a lot of doctors looking at her vocal cords. They thought that was sort of preventing her from breathing properly. That you can have they thought that her vocal cords were getting seized up at some point, and that didn't allow her to breathe very well. Glottal stop is when you close the glottis. And this causes a very particular sound. I'm going to show you a couple of videos. T is the tension. If T goes up, that means that the frequency goes up. That is something that you can change to have either high-pitched sounds are low-pitched sounds. It doesn't cease to amaze you when I do that, does it? Like, I can always see the look of awe on your face when I do that trick. And then mu is the mass density. Okay, this also is fixed. You can't change that. Greater tension will give you a higher frequency. That's the primary way that we change the sound of our voice, by changing the tension in your vocal cords. The length of the vocal cord also affects the frequency. I said this, but let's just write it down. Men tend to have larger larynx. Oh, I'm sorry, a larger larynx. And longer vocal cords. So they have a lower voices. The larynx is important. In fact, the whole size of their head is kind of important. The whole neck region on men is what the neck region for women is important too. But the fact that the neck on men tends to be longer is part of the reason why their voices are lower. And so it's sort of like with a whistle. If I make the cavity bigger, then that makes the sound lower. And that's sort of true for the neck. That when you have a bigger neck and your larynx is bigger, just sort of the whole space is bigger, it tends to give you a lower voice. And if it's shorter and the larynx is smaller, then it gives you a higher pitch. Okay, so the size of the cavities that are involved, and then also the length of the vocal cords will give you either a higher or lower pitched voice. The amplitude of the sound, remember, not related to frequency. The amplitude is only the volume. So the amplitude of the sound is governed by the amount of air that flows past the cords. That's why when they tell you to sing, where are you supposed to breathe from? You're really supposed to use your diaphragm to push so you get a greater volume out of your voice. If you're pushing more air out you're pushing a greater flow of air past your vocal cords. Okay, so the amplitude is governed by the amount of air that flows past the cords. You remember the Bernoulli's effect? We talked about that. Remember about the hairdryer? Bernoulli effect? That said, Bernoulli effect was this effect that we use for airplane wings. And if I have two flows of air going across the airplane wing, if the velocity is high, then the pressure is low. So high velocity gives me low pressure. Which is going to be the higher velocity on the wing, the top or the bottom? The top, right. So this is high velocity, low pressure. This is low velocity, high pressure. So that's going to give me a net pressure that is upwards. That's called a lift. And that's true in your vocal cords too. That if I put a high velocity stream of air between them, it creates a low pressure in between the vocal cords. And it will cause them to sort of come together. Watch this. You ready? Imagine these are your vocal cords. Not a perfect example because your vocal cord is actually fixed on either end. But if I put a high velocity stream of air, what do you think is going to happen to the two pieces of paper? Sort of fly apart? Like that? All right, let's try it. Do you see that? Watch. And the harder I blow, the more they want to come together. Because I create that high velocity air, you would think it would just push them apart. But that's not true to actually pull them together. Have you ever been driving on the interstate and you pull up next to a big 18-wheeler? What happens to your car? It tries to pull you in. That's because of the Bernoulli effect. That you have this high velocity air going between the two surfaces, and it'll tend to pull you together. Tell your friends about that next time you're on the interstate. Say, hey, that's the Bernoulli effect. And they'll say, wow, you're really smart. Okay? So the Bernoulli effect will affect the cords as well. So muscles will bring the cords together. They are muscles, in fact. So that they're closed. So now they'll be closed completely. But then air flowing will sort of push the cords apart. Not the Bernoulli effect, but just the mechanical effect of the air will push them open so that the air can escape from the lungs. However, then the low pressure, due to the Bernoulli effect, that means that if I have a high velocity, I have a low pressure, that will cause them to come back together. This low pressure oscillates. As it goes through, so it'll bring those cords together, the air will force them apart, bring them together, force them apart, bring them together, and then you get a vibrating string. Just like on a guitar, when you strike a guitar, you get a vibrating string. That's effectively what causes your vocal cords to vibrate. That coming together and going apart as the air from your lungs goes through them. And then I mentioned this, but the sound produced by the vocal cords is also changed in a complex way by the mouth, throat, and nose. So you can change if your neck is different in some way, or you can hold your nose and then you'll sound a lot different. Like you'll sort of sound like Urkel. You remember Urkel? You remember that show? Yeah. You don't remember that show. You weren't even born when that show came out. Oh, reruns. Right. Okay. All right, let's look at hearing. So, oh goodness, did I not have? Oh, I'll show you one later. So in a couple pages, I'll show you a picture of the whole speech production system, the larynx and the trachea and all that in the lungs. I'll just ask you to know the different parts of that. Likewise with the ear, on the test, I'll give you a picture of an ear, and you'll have to identify the parts of it by name and then also by purpose. So just know the different parts of the ear. At a basic level, all our ears do are detect vibration. But they're really quite remarkable in the way that they do that, and the great sensitivity that they have, and just sort of the duration, the length of time that we can use them. Really, I think the human ear and the human eye are like nothing else that we've yet to make. And in fact, we tend to model all of our sound detection instruments and our sight instruments, our things to detect light, after the human eye and ear. We want them to act like the human eye or the human ear. And they just don't. They're not really the same. They can't detect the same frequency, the same range of frequencies, 20 to 20,000 hertz. That's a huge range of frequencies for a single instrument to detect. And they don't last as long. A human ear can last for many, many decades. And an instrument you have for a couple of years and then it's no longer really viable. So the human ear is really remarkable in the way that it detects sound and transfers that information to our brain. Ear has three parts: the external or the outer ear, the middle ear, this is called the tympanic cavity. You know what a tympany is? Who knows what a tympany is? Those huge drums that they have in concert bands, the big kettles, they look like brass-looking kettles with a big head on. The tympanic cavity, and then the internal are the inner ear. We'll label different things on here soon. The outer ear includes the auricle, and the auditory canal. It's everything up to the tympanic membrane. The auricle, do you know what the auricle is? It's the floppy part of your ear out here. So the auricle is also called the pinna. And the auditory canal, this is the auricle. This is the auditory canal. You shouldn't put anything into your auditory canal, right, speech therapist? Right. Nothing, I've heard nothing smaller than your elbow is what they say. Do you do that? Do you never put anything smaller than your elbow into your ear? I can't get my elbow into my ear. But you're not supposed to put anything into your ear, like Q-tips and the like. I know we like to use Q-tips, right? It's sort of addictive, but it's not good for you. It can push earwax down into your ear and damage your eardrum. The auricle, I think I write this later. Oh, no, here we go. So it's the visible part of the ear. It directs sound waves of a particular frequency. To the ear, or to the ear canal. So the shape of the auricle, like all these funky folds and stuff, are really cool because they're able to collect particular frequencies. The frequencies that are within the audible region, that 20 to 20,000 hertz. The most common frequencies that you hear is the shape of it. They would collect those frequencies and sort of funnel them down into the auditory canal. It just makes you better at hearing. So the auricle does serve a purpose, and the shape of it is very much a purpose. The ear canal is about 1 inch long. It's open at the auricle and closed at the eardrum. And it works to amplify. So a sound wave coming in right here will have a bigger amplitude by the time it gets down into like it actually amplifies or increases the volume of a sound wave as it comes into the ear. Okay? The middle ear includes the eardrum, and 3 bones called the Auditoryossicles. Here's a picture of the Auditoryossicles. They're the malleus, the incus, and the stapes. That's not a very good picture. I think this is the malleus, and this is the incus, and this is the stapes. The stapes sort of looks like a stirrup that you put on the back of your boots. The malleus, I think it's called. It sort of looks like a mallet or a hammer, and the incus, I don't know, it sort of looks like a bone. These are the smallest bones in the human body. Fun fact, did y'all know that? The smallest bones are inside of your ear. Yeah, they work as a sort of lever, like we talked about in chapter 2, where a lever can take a small force and make it into a big force. That's what they do, is that they take a very small force from the eardrum, and then they make it into a bigger force that will transfer those vibrations to the inner ear. The middle ear also has the opening to the larynx, or excuse me, the pharynx, called the eustachian tube. This is to equalize pressure for the atmosphere. This can get blocked with mucus and inflammation. You know what happens when you get sick? Or specifically, if you're a kid and you get sick, what happens? You what? Snotty nose. And the snotty nose, all that mucus inside of your head will cause you to get the eustachian tube blocked up, and then you're not able to equalize pressure. So when you're sick, that's why you sort of walk around like, it's all congested. It feels like your ears are popping. It's because you can't equalize that pressure between the middle ear and the rest, like the outside world. There's this opening that goes through it. Kids who get sick a lot because they're sort of building an immune system, they'll often have issues with their ears. That's why they get ear infections a lot, because that eustachian tube gets blocked up, and then they get a bunch of mucus behind their eardrum, and it causes it to be infected. You speech people might. Y'all do hearing stuff too? You speech people, or you just speech? Huh? Okay. I've heard this. I don't know if it's true, so y'all tell me. Is that for adults, our eustachian tubes are like this, so they drain very easily. But for children, their eustachian tubes are more like this. Huh? They're really the opposite way?
It's more like poison.
Okay, so they're just not easily drained, right? I was right. I feel very vindicated. Thank you. So anyway, the eustachian tubes, when they say that a kid gets tubes put in their ear, that's what they mean. Like they provide an alternate path for this mucus, this drainage to go out of their ear. The eardrum is also called the tympanic membrane. It vibrates when sound impinges upon it. Okay, I think that's all for the middle. Oh no, we have a little bit more about the ossicles. Know the different parts of the outer ear, that's the auricle, or the pinna, I'll just say auricle, and the ear canal. Know their parts, know their purpose. The auricle is to collect sounds of certain frequencies. The auditory canal, or the ear canal, is to amplify that sound. And then the three bones, let's see, we'll talk about that now. They're going to increase the force of the tympanic membrane. Anyway, so the auditoryossicles. These are three small bones. The malleus. This is a hammer or a mallet. It's not an actual hammer, but it looks like a hammer, whose handle is connected to the eardrum. The incus looks like an anvil. I'm not going to ask you to identify these by sight, but I might ask you about the names, just the malleus, the incus, and the stapes. But it looks like an anvil. And then the stapes looks like a stirrup. And there was a picture of them on the first one. The ossicles transfer vibrations from the eardrum to the inner ear. And it works like a lever. So if I have a lever like this, if I put in a small force here, then I get a big force out here. And it's very much the same way. They just act like a lever. And these pressure, the vibrations, are increased by about 20-fold. Okay? So now be able to name the ossicles. If I show you a picture, just be able to say, oh, those are the ossicles. You don't need to know. You don't need to be able to identify the 3 separate bones, but just know that those are the ossicles if I show you a picture. And then know what they do. They increase the pressure or the force of the vibrations that is then passed on to the inner ear. The inner ear is even more complex. It has 3 parts: the cochlea, the vestibule, and the semicircular canals. We'll mainly look at the cochlea, but we'll sort of lump the vestibule and the semicircular canals together. The cochlea is a fluid-filled chamber that receives pressure waves from different pitch sounds. I'll show you a video, but those 3 bones are oscillating. When the eardrum oscillates, then that pushes on the bones, and then those ossicles will then push onto the cochlea, and they transfer the vibrations from the eardrum into the cochlea. These waves cause the basilar membrane this is like an oval window. Again, I'll show you a video here in just a second. You'll be able to see it, or an animation of it. And then fibers in the basilar membrane stimulate hair cells that are connected to the auditory nerve to the brain. So the cochlea takes vibrations and turns them into an electrical signal. That's its basic function. It's to turn vibrations into an electrical signal, which then goes via the auditory nerve to the brain. Let me show you a video of this. It's just an animation, but it has some more explanation about it.